Hello, everyone, and thank you for coming to our presentation today. My name is Parker Johns, and my partners on this project were Jeremy Crane and Aaron Rapley. And today we're presenting on the design of a small-scale incubator for temperature control of a bacteria sample on a microscope stage. During our presentation, we'll talk about the background for this project, as well as the physics-based model used to describe the system. We'll also discuss the FOPDT regression fit we did, as well as how we calculated our PID parameters, and then the final PID controller performance. And to start off, we'll begin with the Rapley with a video starring Aaron Rapley.
For our project, we decided to solve a problem in Dr. Pitt's research lab involving this microscope. For one of the lab experiments, samples need to be examined periodically during an incubation period. For this to happen, microscope slides must be taken back and forth between an incubator that has a constant set point temperature of 37 degrees Celsius. However, taking the slides back and forth between the incubator can cause disruption in the sample placement and temperature. In order to solve this problem, we 3D printed a microscope cover, attached a heating pad and a thermistor, and created a temperature controller that maintains the 37-degree set point. The apparatus is able to stay in place even with movement of the microscope tray. The cover does not need to be removed at any time during the experiment, and the microscope slide can be seen through the bottom of the tray or on a digital monitor on the side. This solution allows for more accurate temperature control and overall simplifies the actions its research lab.
So in that incubator that goes on the slide, we developed a physics-based model in which we determined that the majority of the heat transfer would be occurring through radiative heat transfer as well as from the heater pad within the incubator. And here we have a doublet test that we took, which shows some of the characteristics of the heat transfer, such as you can tell as the heater is on, as the heat is increased, the slope of the temperature line is higher than when it drops back down. And that shows that there's more faster heat transfer from the heater than the heat transfer from radiation to cool the incubator on the slide. And on the next, here we have the FOPDT regression fit, in which we match that doublet test from the previous slide with these FOPDT parameters. And here they are for your convenience. And so from there, we were able to calculate our PID parameters using aggressive, moderate, and conservative tuning. So the tuning that we ended up settling on was the aggressive tuning, but we tested it out with the conservative and the moderate first because we wanted to avoid overshoot. So it didn't end up being much of a problem. We ended up preferring the fast response time because overshoot wasn't that extreme. And so here we have our KC value that we're using is the 21.76, and then the integral time constant is 383.3, and the derivative constant was 0.0172.
So here are the results from our PID controller. You can see, like Jeremy mentioned, we used the aggressive PID control because the other controllers were just too slow. And you can observe that there was no delay in the temperature response from when the heater was turned on. The rise time to reach our set point of 37 degrees Celsius was about 8 minutes. And then the peak time was about 10 minutes to reach a temperature of about 40 degrees Celsius. And that's where our overshoot occurred. It resulted in an overshoot ratio of about 0.2 almost. But then there was no real decay ratio after that because the PID controller just brought the temperature right back down to 37 and held it there for almost an hour. But it did take almost 20 minutes to settle onto that set point. And now to end, we'd like to make you aware of the safety considerations we took into account when designing our incubator. We implemented several automatic shutoffs to prevent overheating, damaging our sample, or damaging the hardware and building based on the measured temperature and heater values. So if the temperature ever exceeded 50 degrees Celsius, the incubator would automatically turn off, and the heater value is never allowed to exceed 50% power output. And so with that, in conclusion, we were able to successfully design a PID controller to safely control the temperature of an on-stage microscope incubator for use in bacterial growth experiments.